Okay, let's dive right into this explainer. Today, we're unpacking a truly fascinating case study that, honestly, reads almost like an operational thriller. We'll be looking at how one tiny, seemingly insignificant broken part can completely paralyze a massive, multi-million-dollar mining site. If you've ever wondered about the incredibly fragile mathematics keeping heavy industrial operations alive, well, you are in the exact right place. We're going to break down physical availability and show you the devastating butterfly effect of a single mechanical failure.
To kick things off, we really have to ask a critical question about heavy equipment management. Imagine a sprawling, active mining operation, massive machines moving absolute mountains of earth. What actually happens to that entire synchronized operation when a single air conditioner goes down? I mean, it sounds like the punchline to a joke, right? The operator gets a little sweaty, maybe opens a window. But as we're about to see in the data, the reality is a cascading operational failure that literally costs thousands of dollars by the minute.
To answer that, we first need to understand the metric that rules them all in this industry: physical availability, commonly known as PA. PA is a key performance indicator that shows the exact percentage of time a unit is physically and technically healthy enough to operate. It purely evaluates a machine's technical readiness, totally separate from whether the operational team actually uses it or not. Think of it as the ultimate report card for a site's maintenance planning program. Simply put, if the machine is mechanically sound, your PA is high.
And the foundation of our entire case study today rests on this number right here, 24, specifically a 24-hour scheduled hours framework, which is known as MOHH, or Man on Handling Hours. What this actually means is that the clock is constantly, relentlessly ticking on a non-stop, round-the-clock operation. Every single calculation we do, every percentage point of availability we measure is based on that denominator of 24 hours. There are absolutely no breaks in the math here.
So let's slice up that 24-hour calendar into two distinct categories: available hours versus our ultimate enemy, repair downtime. Available hours are times when the unit is out of the workshop. This combines both the time the machine is actively working and the time it's just on standby. Unavailable hours, on the other hand, are strictly repair and maintenance hours. This is the hard downtime. This is when the machine is technically incapable of doing its job.
To get perfectly clear on the operational drama we're about to see, we have to define three very specific statuses. Working, represented by a W, is purely productive. The machine is actively digging or hauling. Standby, or S, means the machine is completely healthy, but it's halted by non-technical issues. Think heavy rain, operator meal breaks, or waiting in line. And finally, repair, or R, is lost time due to unscheduled breakdowns or scheduled servicing.
All right, with the stage set, let's introduce the main character of our story, the primary loading equipment, a PC 1250-11R excavator. In any mining operation, the excavator acts as the prime mover. It completely dictates the pace of everything else. If the prime mover is digging, the site is making money. If the prime mover stops, the heartbeat of the entire mining front flatlines. You'll want to keep that in mind as we look at what happens next.
And here is our inciting incident. The operation sets a really strict target physical availability of 90% for our prime mover excavator, but the actual PA suddenly drops to 85%. Why? Because of a sudden unscheduled breakdown. Remember that air conditioner we mentioned? Well, it turns out a leaky AC condenser caused the system to run incredibly hot, forcing the unit to be shut down immediately so the part could be replaced. Now, a 5% drop doesn't sound like a disaster, does it? Let's look a little closer.
When physical availability drops to 85%, it means 15% of our 24-hour MOH is entirely gone, and that translates to exactly 3.6 hours of hard downtime. Those 3.6 hours are consumed by a very rigid sequence. First, the mechanic has to conduct an investigation to actually find the leak. Then comes parts ordering to go get a new condenser, and finally, the actual execution of the replacement.
Let's translate that time into sheer volume. Because the excavator is the prime mover, losing 3.6 hours isn't just a headache for the mechanic, it's a massive hit to production. This specific loader operates at an assumed productivity rate of 805 bank cubic meters, or BCM, per hour. So if you multiply 805 by those 3.6 hours of downtime, bam! Exactly 2,898 BCM of production vanishes instantly from the daily target. That is earth that simply does not get moved today.
Okay, let's switch to the other side of the operation and see how this builds. We have our prime mover, but it obviously needs a supporting cast. That cast is the hauling fleet, specifically composed of 10 massive Komatsu HW70 haulers. These are the giant trucks that line up to catch the dirt the excavator digs out, and their performance is monitored just as tightly as the excavators. Now, plot twist, the haulers are actually outperforming expectations. Their target PA is also 90%, but they are currently sitting at a massive 95% actual physical availability. Out of the 10 trucks, only one single unit is in the shop, and it's just there for perfectly planned, scheduled, routine maintenance. No surprises, no sudden breakdowns. The maintenance team for the haulers is absolutely nailing it.
So, here's the crucial point. Having exactly 9 healthy, ready-to-go haulers isn't a problem at all. It's actually perfection. Based on fleet sizing and the distance they need to travel, 9 HW70 haulers create the absolute ideal match factor to balance the capacity of our single PC 1250 excavator. The setup is flawless. The haulers are ready. The system is perfectly primed for maximum efficiency.
But here is where the domino effect strikes. We've got 9 perfectly healthy haulers ready and revving. But remember our prime mover? The excavator is completely dead in the water, getting its AC condenser replaced. And because the excavator is down, those 9 haulers are entirely paralyzed. The front has totally collapsed. That perfectly planned match factor suddenly means absolutely nothing.
For the entire 3.6 hours that the mechanic is replacing that condenser, those 9 haulers are just sitting idle. Their operational status is forcefully shifted from working, which is productive, into standby, and they get tagged with the dreaded delay code, waiting loading equipment. They are technically 100% healthy, their PA is super high, but they are completely useless because the prime mover has failed.
If we zoom out to the final consequence here, the picture is pretty grim. What we're seeing is how a tiny, microscopic failure, literally a leak in an air conditioning condenser on one single machine, creates a massive, macroscopic financial bottleneck for the entire site. It's the ultimate operational butterfly effect. One mechanic turning a wrench on an AC unit means an entire fleet is frozen in time.
Let's quantify that pain for a second, because the financial ripple effect is huge. First, the metric known as use of availability, or UA, for the hauler fleet just plunges, because they simply aren't being used. Second, the company has to absorb massive depreciation and idle costs for 9 giant haulers that are just burning fuel and doing absolutely nothing. With zero material being moved during those 3.6 hours, the shift's cost per BCM ratio is completely destroyed.
As the source material perfectly summarizes, this single leaky condenser creates massive inefficiency. But here's the thing. Operations don't just accept this kind of loss. This is exactly where the maintenance planner steps in for some critical post-incident actions. They investigate the root cause, discovering, for instance, that material fatigue actually caused the leak. Consequently, they go into the system and update the condenser's lifetime settings, actively scheduling preventive replacements before they ever fail mid-shift again. It's a stark reminder that in heavy industry, technical health and operational success are deeply intertwined. As we push for higher targets, we have to constantly fortify the fragile math keeping our operations alive. Thanks for joining me on this explainer, and I'll catch you next time.